Okay, so next part of the video, we're going to discuss the non-homogeneous linear differential equation with constant coefficient. Okay, right, so if you're given this ODE and you have this the part where it is non-homogeneous is the right-hand side part here, r of x. So if r of x is in the form of exponential, polynomial, sine and cosine function, or a combination of exponential, polynomial, sine and cosine by addition, minus and multiplication, then we can use this method called the method of undetermined coefficient. But other than that, if the Rx is other than the combination of these through addition, multiplication and subtraction, then we cannot use the method of undetermined coefficient. Okay, so right, so let the right hand side Rx be equal to e to the alpha x times the polynomial of x to the nth degree. Okay, so then we can obtain this. You just substitute this Rx with this function. So you have the right hand side equal to a combination of exponential and polynomial function. So this p and x is the polynomial function with degree n, the power lah, the highest power that the equation is being raised to. Okay, hence we can propose a particular solution for yp equal to e alpha x qn of x. So because remember when I talked about it earlier in the earlier part of this video, so for non-homogeneous ODE, you gotta have two solutions, which is the complementary and particular solution. So the YC, you can get the YC by solving the homogeneous part of the ODE, i.e. using the characteristic equation. However, this part we're going to find out how to find the YP using the right-hand side of the ODE, which is not equal to 0. So we will propose a particular solution YP equals to this depending on our type of Rx. Okay. Okay, so the general procedure for the method of undetermined coefficient. So this you need to follow the step by step. Given the ODE in a general form like this. Okay, this is the general form: a d2y dx squared plus b dy dx plus cy equal to Rx. So first thing first, we need to solve the homogeneous part first, which is the YC. So this one you use the characteristic equation and find out the m depending on the value of m, whether it's distinct real roots or complex conjugate or repeated real roots. Then you get the yc equals to y1 plus y2 depending on the function. How to oops, what is this? How to okay, right, sorry about that. And step number 2, after you solve the homogeneous part, then we want to work on the non-homogeneous part, YP. So here, right, so this is your right-hand side, the Rx. So given E alpha x and Pn, so we want to find out what is the Qn here. So the proposed particular solution is thus Yp equal to E alpha x. We bring it together. I mean, we just bring it down, and the different thing here is the Qn. So what is Qn? We're going to look at the next slide. But before that, after we propose to YP, we need to check if YP and YC are linearly dependent or not. If it is linearly dependent, then we need to put extra effort. We need to give a treatment or cure to the YP to obtain linearly independent solution. Okay, so one of the method is you can put extra x term, or if it's already have if your YC already got the XE mx term, then you need to put another x term to become x squared instead, so that the YP and YC will not be linearly dependent. And after you have made sure that YP and YC are linearly independent, then we want to solve for the undetermined coefficient for the particular solution only by comparing the coefficients on both sides of the equation. So that's why this method is called the method of undetermined coefficient. Okay, because we need to determine the coefficient. And finally, the total solution for the second order ODE is a combination of YC and YP. Okay, so then only your job is done. All right, so some hints here before we work on the example. Always solve the complementary solution first before proposing the particular solution. Okay, and the method of undetermined coefficient is only applicable to second order non-homogeneous linear ODE, where the right hand side components are restricted to this type of function as I mentioned earlier. Okay, and the exponential function is directly related to this term, and the polynomial is this term. However, you can also use sine and cosine to relate it to the exponential function, because you can use this Euler's formula. So this is a general Euler's formula where I previously asked you to go through appendix 12.1 to see how it's being used to convert for roots containing complex conjugates. Okay, so just take care of this. Okay, Euler formula. So we can convert cos and sine into exponential of something times x. Right, so let's just do a quick exercise or example on the Euler formula. So you know that given the Euler's formula, e to the power of plus minus ix equals to cos x plus minus I times sine x. So if e ix, then it's just cos x plus I sine x. But if it is e minus x, then cos x minus I sine x. So what if you have e to the power of negative I times 10x? So just replace this x with 10x and this x with 10x. But since it's negative, thus you take the minus sign to be in the middle. So you can see that in this case, you have real part and imaginary part of this exponential term. So the real part, so the imaginary part, okay, because here it shows the imaginary part here. So IM stands for imaginary. So imaginary part of the exponential of negative I times 10x is the one containing the I. So this is the imaginary part. So the imaginary part is negative sine 10x because it contains the I term here. Whereas the real part of the exponential of negative I times 10x, so you can put RE stands for real. So the real part of this term is just this cos 10x. Okay, so let's do a quick exercise. What is the imaginary part and the real part of e to the I times 5x? So you can convert that into Euler's form. Using Euler's formula, you can convert it into cos and sine notation. So e I 5x equals to cos 5x plus I sine 5x. So imaginary part of this e times I to the power of I 5x is the sine 5x, whereas the real part of e I 5x is cos 5x. Okay, so it may not be as useful now, but we have to know and identify what is real and what is imaginary after this, as we are converting the cos into the exponential term. Okay. Right, so let's see some possible particular solution proposed for the second order non-homogeneous linear ODE. Okay, so proposed YP. So given this function, so this is the normal function, the homogeneous part, but here is the non-homogeneous part. So for different types of Rx, then you can propose different types of YP. Okay, so in general, Rx is your Rx is of the form e alpha x times the polynomial of x to the degree n. So you can propose your YP of x as e alpha x times qn of x. So q is another function of x to the same degree of polynomial with the p. All right, so let's have a look at number one, where you have Rx equals to e to the power of negative 3x. So this is a pure exponential function, simple one, yeah, the most simple stuff. Here you can propose yp equals to, you need to put a constant here because you don't know what times what. It could be just 1, but to be safe, just put some constant here. So you just follow, because this is the alpha here is -3. So just put here exponential of -3x times a. And in this case, since you don't have anything multiplied with the rx, so your qn of x, so the n here is equal to 0, because it's just a polynomial to the degree of 0, which is just 1, just times 1. But we just ignore this one. So we propose yp equals to a times e to the power of -3x. So example number 2, if you have pure sine function, so sine 5x. So this sine 5x, you can make use of the example that we did previously here. So sine 5x is actually the imaginary part of the exponential of I 5x. So that's why you can propose the yp to be equal to a constant a times e to the power of 5ix. Okay, because it's sine 5x. So we just make use of the Euler formula here, or Euler notation here. So for sine 5x, it's actually equal to ei 5x, but it's just the imaginary part. So but we can just put yp equals to a times e 5ix, but the actual yp is just the imaginary part of the yp, imaginary part of the e 5ix. Okay, another example here, number 3, is if you have rx equals to cos 6x. So here is a pure cosine function. So also still making use of the Euler's formula. So for cos 6x plus I sine 6x, this is equals to e 6ix. However, because it's just the cos, so it's the real part. So the actual yp is the real part of the proposed yp. But you can just use the exponential here to just make your life easier, just to proceed with the calculation. But at the end, when you want to compare the coefficient, you just take the real part of the yp. Okay, so number 4, this is a bit complicated when you combine exponential and cosine function. Okay, so here your rx is a combination of exponential and cosine function. Yeah, let me show this one in the whiteboard. So just bear with me. Whenever I exit the slideshow, it's just gonna jam a bit. So if you, oops, jumped it. Right, so now if you have this thing here, I mean the rx is a combination of exponential function e to the 3x and cos 6x. So you can write down e 6ix equal to cos 6x plus I sine 6x. So this cos 6x is actually the real part of e 6ix. Okay, so you can propose your yp to be equal to a times e 3x times e 6ix. But bearing in mind that the actual yp, you will only take the real part of the e 6ix, not including the I sine 6x here, okay? So when you combine this term, you can propose your yp to be equal to a times e 6i minus 3 times x. So that's why your proposed yp here is shown as such. Yp equals to a times e to the power of 6i minus 3 times x. Okay, continue. Next is if you just have pure polynomial function. Okay, so your rx is just a pure polynomial function. So here your alpha is just 0 and then your Pn, your n is equals to 3 because it's to the power of 3, then you need to propose a Qn with the same degree of polynomial. So you propose yp equal to ax cubed plus bx squared plus cx plus d until until to the very last power of 0, which is just 1. So that's why you got the d here. Okay, so you need to follow through until you get, although these original Rx don't include the term x, it just from x squared directly to 5, but then you need to follow through the order from x cubed, x squared, x, and finally x0. Number 6, if you have a mixture of polynomial and exponential function by multiplication, so in this case, your alpha is equals to -3 and your n is 1 to the order of 1. So here your yp is e alpha x times qn. So your qn polynomial is to the power of, to the degree of 1. So that's why you need to propose ax plus b as the qn for the yp. And number 7, if your Rx is a mixture of polynomial and exponential function by addition. So this is polynomial, add with a, this is exponential, add with a polynomial function. So this one you can split them into 2. Okay, so this is one part and this is second part. So you can propose yp1 to respond to the polynomial. So since the polynomial here is of a degree 3, so you propose another polynomial of the same degree 3, and another part is for the exponential. So you maintain the same value of alpha, but you put another coefficient in front, but the total yp is equal to yp1 plus yp2. So it is easier this way. It can be solved separately and you can combine the result later. Okay, so these are some suggested possible particular solution of yp given the different forms of Rx at your right hand side of the non-homogeneous ODE. Okay. Yeah, there's another alternative method. If you don't want to use the Euler's notation, you can use this to propose the particular function for the right-hand side where it involves sine and cosine function. So yeah, let's do this. So if you are given any cos or sine function, you can propose to yp to be this type. Okay, so let's do this example. Okay, do this example. So in this example, if your Rx on your right hand side is equal to sine 5x, so you can propose, okay, number 1, okay, for Rx equals to sine 5x, then your yp, proposed yp is c cos 5x plus d sine 5x. So you don't have to identify the real part of the imaginary part, because previously if you use Euler's notation, you write down e to the 5x equals to cos 5x plus sine 5x. Thus sine 5, okay, so sine 5x is the imaginary part of the e to the 5ix. But if you don't like to, to have to identify real and imaginary part, then you can use this other method where you propose yp equals to this. And number 2, if your Rx is equal to cos 6x, then your yp is just c cos 6x plus d sine 6x. And number 3 also, so your Rx is equal to e to the 3x times cos 6x. Then here you can break down the yp into 2 parts. So yp1 is for not two parts, meaning the combination of this yp. So the exponential part, you put a e negative 3x, and the cos part, you can put c cos 6x plus d sine 6x. So this is actually, this example 3 is similar to what we have in number 4 here. You see this one? So this yp is actually the same with this yp, but it's written differently. This is an alternative way to write a yp. If you don't like to have to identify real or imaginary part of the yp, then you just deal with this form instead. Okay. Right. What's next? Right. So we are only in step 3. So how many steps do we have? So first, solve the homogeneous part. Second is the yp. So step 3 is to check whether yp and yc are linearly dependent, because the total solution to the non-homogeneous second order linear ODE is yp plus yc. So yp is what we have discussed lengthily just now to choose what are the possible possible forms of yp. And then after you have decided on a yp, then you need to check whether the yp and yc are linearly dependent. So there are some shortcuts to quickly see whether your yp and yc are linearly dependent or not. So because your right hand side, so because your for your ODE, right? So your right hand side, the Rx general form is E alpha x times the polynomial of x. So look at the value of alpha in the Rx at the right hand side and check if alpha, M1 and M2 values. Okay, check the alpha values M1 and M2. So M1 and M2 are the, when you solve for the homogeneous part, right? When you do the characteristic or auxiliary equations just now. So if your value of alpha is not the same with M1 and M2, then you can be sure that your yp and yc are linearly independent. However, if your alpha is equal to either one, M1 or M2, and M1 is not equal to M2, then you need to propose another form of yp such that it's not linearly dependent to any one of these M. Okay, and number 3 is, let's say your M is a repeated real root, so M1 equals to M2, and so happen that your alpha is also equal to M1 and M2, then you need to also propose another form of yp. Okay, so now this is step number 3. You check whether yp and yc are linearly dependent. So this is what I just mentioned. So this table just summarized it. So for case 1, alpha is not equal to M1 and M2, so you just follow lah. Okay, you don't need to do any modification to the yp. But let's say your M1 and M2 are two distinct roots. However, your alpha is equal to one of the coefficient, either M1 or M2. So depending on which one is it the same with, so you need to put the x to the alpha that is the same to the another one. So I mean, you just put an extra x in front lah, so that it's not the same with any of these terms. Okay. And the third case is if you have M1 equals to M2, i.e. the repeated real roots, and it so happen that your alpha is also equal to M1 and M2, then okay, so initially your YC already have this additional x term, and now your YP need to add x squared instead of just adding x in case 2. So because if you just add x, then it would still be linearly dependent to this solution. So it doesn't work that way. So you need to put this x squared here. Okay. Right, so break before we continue to the next section of the video.